Welcome. This is lecture 13 on depth first search. So first, let me remind you where we were from last time. We were talking about graph algorithms, and in particular about exploring a graph, sort of the most basic thing we need to do with graphs. And lastly, what we looked at is breadth first search, which is sort of a cautious search. It looks at everything from where it is, like all the neighbors of vertex 1, before proceeding to the next vertex, which in this case would be 2. It stores vertices in a queue in order to do this, and it ends up finding levels of the vertices, which have the property that we are finding shortest paths from the start vertex to every other vertex. Now, the first thing we're going to look at today is another way of searching a graph, depth first search, and this is more like a bold search. It goes as far as possible in its exploration before backing up to find if there's anything new. So let's look at this example. We're going to start the depth first search at vertex 1, and we would then look in the adjacency list of vertex 1 and say, okay, vertex 2 is the next thing that I find. So vertex 2, and now rather than exploring other neighbors of vertex 1, we now look at the adjacency list of vertex 2 and say, okay, vertex 5 is what I find next. Now from vertex 5, we look in its adjacency list, we see vertex 2, which we've already discovered already. The next one we find is vertex 6. So from 5, we find vertex 6. Looking at neighbors of vertex 6, it's only vertex 5, and we've already seen that. So now we are done with vertex 6. We back up and we come back to vertex 5. We got as far as this in the adjacency list, so next we look at vertex 7. So from vertex 5, we find vertex 7, and from vertex 7, we found all of its, we found one neighbor here is the one we already found. The other neighbor is vertex 2. So I'm going to mark that as an edge. It's, as with the breadth first search tree, there are some edges we discover here that are not going to be part of the depth first search tree, and I'm going to mark those with the dashed edges. Now at this point, we have completed vertex 7's adjacency list, and we back up then to vertex 5 and discover that we are done with it. So we back up to vertex 2. We have seen the neighbor 5, the neighbor 7, we have now found already as a dotted edge, and the next neighbor is vertex 4. So I find vertex 4. I look in vertex 4's adjacency list and I find vertex 3. I look in vertex 3's adjacency list, I find vertex 1, so that's going to be another of these back edges. And I find vertex 4, which I've already seen, and vertex 2. So there I have another back edge. And now I am done with all of the neighbors of vertex 3. There were 3, and we have all 3 edges. And now I back up to vertex 4 and continue exploring there. I have found the neighbor 3. There's a neighbor 1. So that will be another edge to something we've already seen, in other words, a back edge. And vertex 2, which was the parent, which I've already done. So now we are done with vertex 4. We back up to vertex 2. We have found vertex 4, vertex 3, I've already seen that edge, and vertex 1, I've already seen that edge. Now I finally back up to vertex 1, and I say, oh, all 3 of these things I have discovered. So this would be the complete depth first search tree. And just to emphasize the order in which we explored things, I went as far as I could to vertex 6, and then I backed up and started looking from vertex 5, backed up, tried vertex 2 some more, went as far as I could, and finally backed up and came sort of back out of my recursion, if you like, at vertex 1. Now, one thing I'd like you, let me add here the order in which these vertices are discovered. So vertex 1, then 2, 5, 6, then 7. And then I came down from 2, vertex 4, vertex 3. That's the total order. And it's also good in the depth first search to pay attention to the order in which we finish the vertices. And that is that vertex 6 was the one I finished off first, then vertex 7. I backed up and finished 5. Then I finished 3, 4, 2, and 1 finally at the end. Now, I've put a couple of notes here. One is that the order in which we discover things and the shape of the tree, it depends on the ordering that was in the adjacency lists. And the other thing is moving forwards towards our pseudocode. Whereas in breadth first search, we used a queue, and that's what governed our search by the levels. In the case of depth first search, we're using a stack to store vertices, the ones that we have discovered but not yet explored, essentially. Okay, so let's look at the pseudocode for this. I have written here depth first search as a recursive routine. In other words, the stack is implicit. I'm not explicitly pushing and popping from the stack. So as a recursive routine, when I'm searching from a particular vertex V, I will start off by marking that I've discovered it. And then I look at all of its neighbors. And so I look in the adjacency list of vertex V. If I find a vertex U, a neighbor of V that is undiscovered, that's when I recurse and do a depth first search of vertex U. I've left a little space here because we're going to add some things to this code. Now, here is the top level code for depth first search. And the point of this is when I do not have a particular vertex I want to start with, I just want to explore the whole graph. So I believe that for breadth first search, I left it as an exercise to give the main routine that would find all the connected components. And in the case of depth first search, here I'm giving it explicitly to you. So we would initialize by marking every vertex as undiscovered. And then for every vertex V, I say, oh, if it's undiscovered, then I'm going to start a depth first search tree rooted at that vertex. So I'll run the depth first search tree of V. It will discover for me everything that is connected from vertex V. But in case the graph is disconnected, I will come back to this loop and be checking other vertices and potentially find another tree. So I may eventually have some kind of structure where I find one tree, and then because the graph is connected, I find another tree later on. Okay. Now, as with breadth first search, we should store more information than just going through this routine. This routine doesn't actually collect any information as we go. So what we're going to do is store the parent pointers so that I explicitly know which edges are in the tree. And we are also going to label edges as being either part of the tree or not part of the tree. And we could also, in cases like this, store component number. So I would say this is component 1, this is component 2, and I might like to record for every vertex which component it landed in. So let's look at what I would do to collect the information about parent. Now, when I find here vertex U being undiscovered, that is when I'm adding something to the tree. So I would set the parent of vertex U is vertex V. And I also now have an edge of the tree. The vertex from V to U is a tree edge. Okay, it goes from the parent V down to the child U. And then in this case, I'm calling depth first search, but otherwise here, I have an else statement after my if. In this case, I have either a back edge or I'm looking at the parent itself. So I have to escape from that. If U is not equal to the parent of V, then I'm going to mark that VU is a non-tree edge. And I'm also going to explicitly mark a vertex as being finished when I'm done with it. Okay, and in a little bit, we're going to think about the order in which we discover vertices, but also the order in which we finish with the vertices, as we marked on the previous slide. If you remember, this was the order in which the vertices are finished, and that ordering is going to be very useful for us. Okay, so on the next slide, I simply have the blue parts marked here in the code, and we're going to talk about the runtime analysis. And I claim that it's order n plus m. If you remember, n is the number of vertices in my graph, and m is the number of edges. Perhaps I don't have that written down yet. So n is the number of vertices, m is the number of edges. And the way we prove that this is the runtime, it's the same analysis that we had for breadth-first search. Essentially, we are looking for every vertex once we are looking through its adjacency list. And we argued that this is the sum of all this work is order m, the number of edges, because every edge appears twice. The edge from U to V appears once in U's adjacency list and once in V's adjacency list. So the total amount of work for going through all the adjacency lists is 2 times m, in other words, order m. And that was the argument why the runtime is in total n plus m for doing a depth-first search. Now, I've left as an exercise to do the other useful thing I suggested we might do, which is to number the connected components in case there's more than one, and to record for each vertex which component it belonged in. Okay, so some of the properties of depth-first search, it gives us quite a lot of structure. First of all, it partitions the graph into one tree for each connected component. Breadth-first search would do that too. Secondly, we can classify the edges. So far, I've talked about tree and non-tree edges. As we go further and consider depth-first search, especially in directed graphs, we're going to further refine this classification on the non-tree edges to say there's different kinds of non-tree edges. And then the other part of the structure we get is vertex orderings, and the order in which we discover vertices and the order in which we finish the vertices. So one of the more basic things we want to know is that if I do a depth-first search from a vertex V0, then I do reach everything connected to V0. That's part of what's claiming that I can find all the connected components this way. So let's look at the proof of this lemma. If there's a path, let's say V0 up to some final vertex, V sub F, if I look at the last vertex of this path that I've discovered, let's say V sub I, then what happens in the depth-first search is I explore and I discover all the neighbors of V sub I, including the next neighbor in this path, right? So that means I will eventually get from V0 to V sub F. A more formal way to do this would be to say that this is a proof by induction, but this is the heart of it. Okay, so the next property we're going to look at is that any non-tree edge joins what I'm calling an ancestor and a descendant in the tree. So to define that, let's look here. I say that a vertex V is an ancestor of U, and the other way to say it is that U is a descendant of V, if I can follow parent pointers from U and get to V. So U is a descendant of V, V is an ancestor of U. As another example here, V is not an ancestor of X because when I follow the parent pointers from X, I get here and I never get to vertex V. Okay, so that's the definition of ancestor and descendant. And what we're going to prove now is this lemma that says any non-tree edge joins an ancestor and a descendant. So let's look at that. Essentially what we're claiming is that I never have an edge like this that goes sort of across the tree between vertex A and vertex B, where neither one is an ancestor of the other. So let's look at this proof. Let's consider some non-tree edge. I'm going to call it AB, but it need not be like in this picture. We're going to prove it can't be like in this picture. Suppose that vertex A is discovered first. Okay, so I have an edge from A to B. So when I call the depth first search at A, as soon as I discover it, I call this, I'm going to examine the neighbor B. And what does it mean to examine that neighbor in the depth first search code? I look to see, is B discovered? So I will certainly discover B before A is finished. It need not happen that we will discover B as a child of vertex A, but we will definitely discover B before we are finished with A because we go through all of its neighbors. So then this means that B appears in the subtree rooted at A. I exhaust that whole search before I'm finished with vertex A. And this means that, so A is an ancestor of B. Okay, so that's the end of this proof. If we have a non-tree edge AB and vertex A is discovered before B, then A is going to be an ancestor of B. One little thing to note about this proof is it's not a proof by contradiction. And I think often when we prove things, we often first think, oh, suppose it's false. And then what can I get out of that? But very often that's more complicated than it needs to be. And you can just directly prove the thing you want. Here we just said, suppose we have a non-tree edge and we directly prove that such an edge joins an ancestor and a descendant. So whenever you're tempted to do a proof by contradiction, first think, can you just prove directly what you want? There are times when we need the hypothesis that the conclusion fails, but those cases are actually sort of rare. Okay, so let's look at enhancing depth first search to explicitly compute the discover and the finish times. So the one thing different here are these lines in blue. I'm initializing time. If I had multiple connected components and we had the depth first search that just tries each vertex in turn as a root, then I should initialize time to be 1 at the start of that. But here I'm just writing the piece of the code that does depth first search from a particular vertex, okay? So I'm initializing time to be 1. And when I discover a vertex, that's when I'm setting the discovery time. D of V stands for discover time. And I update time becomes time plus 1 so that I have only one event happening at each time point. And when do I set the finish time for a vertex? Here was the line in the code where we were saying we're finished with a vertex. So here is where I would set the finish time of V to be the current time and update time. Now, a good thing to notice about the discover and finish times is they have a certain ordering property. In particular, they form a parenthesis system, which I misspelled here. Sorry, system. In particular, suppose that I discover vertex V before vertex U. So V goes on the stack before U goes on the stack. Then either it happens that I discover V and finish V. Oh, there's another typo here. This should be the finish time of V. And then after that, I discover U and then finish U. Or the alternative is that I discover V, it goes on the stack. Then I discover U, it goes on the stack. So at this point in time, they are both on the stack. And then it must be that I finish U before I finish V, just from the stack property. So in particular, if I look at joining discover times and finish times, I would never have a situation like this where they interleave. So this is not possible. Okay, and by this I mean that I discover V, then I discover U, then I finish V, and then I finish U. That is not possible. Okay, that was part one of this lecture. We've talked about depth first search, discover times, and finish times. And you should know how to do depth first search, how to carry it out, how to make use of it, and the property of non-tree edges. Remember what that was? That every non-tree edge goes between an ancestor and a descendant. So the next part of this lecture is going to be looking at an application of depth first search. And we're going to continue this in the following lecture when we look at depth first search for directed graphs. All right, so let's look at this application of depth first search. The application is for finding what's called two connected or bi-connected components of a graph. Now, we've looked already at connected components of a graph. That's when the graph itself is not connected, and we look at the separate pieces as being the connected components. So there's one level sort of further than that, which is to suppose what happens if there's a vertex that I remove from the graph. If I remove vertex 2 from the graph, I disconnect it. And that's a very bad property to have in a network, that it's so fragile that there's a single vertex, which if it fails, the network becomes disconnected. So we do not like to have these cut vertices in a graph. In this particular graph, vertex 2 is a cut vertex, and vertex 5 is also a cut vertex. If I remove vertex 5, I separate this piece of the graph from vertex 6, left all by itself, which cannot connect anymore. So here's the definition of a cut vertex. V is a cut vertex if removing V, well, together with the incident edges, makes the graph disconnected. So this application is to find the cut vertices of a graph, and something a little stronger than that, which is when I have a cut vertex, I can think of it splitting the graph into separate pieces. So these are what's called the bi-connected components of this graph. I imagine removing 2, seeing the pieces that I get, and putting vertex 2 back into each of the pieces I get. Similarly, removing vertex 5, seeing what are the pieces I get, and adding vertex 5 into each of the 2 pieces. So we're going to find the cut vertices using depth first search. And this is the same graph that I had in previous pictures. And I showed a depth first search starting at vertex 1. Here I'm showing a depth first search starting at vertex 5, just so you see that we get a different structure tree if we start at different places. And also, I wanted to show you what happens when this depth first search starts at a vertex that is a cut vertex. So here's the picture of the depth first search starting from vertex 5. And we see the 2 components, vertex 6 and the rest of it, happening because vertex 5 has 2 children. The other cut vertex here, if you look at what it looks like in this tree, one of the pieces I get is vertices 1, 2, and 1, 3, and 4, which are here. And the other piece I get when I remove vertex 2 is this, 5, and 6, and 7, right? So we are going to work at understanding the cut vertices in terms of a depth first search. Now, here's a tiny bit of history of this, together with, by the way, the picture from Wikipedia showing cut vertices done with this fancy coloring system where this vertex is colored red to indicate it's part of this component, and with the cyan to indicate that it's part of this component. So if you like this kind of picture, I thought it was a little bit illuminating about cut vertices. They're the ones with the multiple colors and the components that you get from these cut vertices. Now, this algorithm I'm going to show you, a linear time algorithm to find the two connected components using depth first search. It's due to John Hopcroft and Bob Tarjan back in 1973. And often when people talk about famous computer scientists, and these are two of the most famous computer scientists, they show you pictures of them currently as they look now. Hopcroft is rather elderly now, and Tarjan not quite so elderly, but certainly older than in this picture. What I'm showing you here are photos of them from about the 1970s. So here's Hopcroft, and Tarjan had a beard and long hair. He doesn't look like that now, but I invite you to look at this Wikipedia page to find more current versions if you follow the links. All right, so let's look at finding two connected components. What we're going to do first is to find those cut vertices. And first, we're going to characterize what do they look like in terms of the depth first search tree. So here I've written down in a more precise way what I was telling you about in the previous picture. The root is a cut vertex if and only if it has more than one child. So the reason is the only way the root vertex is going to separate into multiple components when I remove it is if I have multiple children of the root. If I do have multiple children, why does that make the root a cut vertex? The reason is I can't connect across here because remember that every non-tree edge goes from an ancestor to a descendant. So there are no edges that connect here to here. And if I remove 5, I'm separating this from this. So that's what the claim is saying. And as far as cut vertices that might not be at the root, here's the lemma that characterizes that. So a non-root vertex V is a cut vertex if and only if V has a subtree. In this case, vertex 2 has 2 subtrees hanging off it. And there's one subtree for each child of a vertex. So V has a subtree that has no non-tree edge going from the subtree to an ancestor of V. So let's look what that property means here. Vertex 2 has 2 possible children. Vertex 7, the child 7 is in a subtree that only consists of 7. Does this satisfy this property? No, there's an edge going from 7 to an ancestor. So this child does not make vertex 2 a cut vertex. On the other hand, this child, if I look at it, I have this subtree. And is there a non-tree edge going from the subtree to an ancestor of vertex 2? Well, no. All the non-tree edges just go up only as far as vertex 2. So that is why vertex 2 satisfies this property and by the lemma is a cut vertex. So let's look at the proof of this lemma. It's not difficult at all. If I have this property that vertex V has a subtree, let's look at V. So I have various children, and each of those children leads to a subtree. And remember that we have no edges like this. Okay. No edges crossing between the subtrees. And let's look at where some of the other non-tree edges might go. I might have one going like this. I might have here just some that go to here. And here I might have some that go higher. What we're supposing for the first direction of the proof is that V has a subtree T with no non-tree edge going from the subtree to an ancestor. So that would be this, for example. Here is my subtree T. And in this case, when I'm removing V, separates that subtree from the rest of the graph. Okay, depending crucially on the fact that there are no cross edges here, none of these red edges. Okay, so that proves the one direction. And for the other direction, we want to suppose that we have a non-root vertex V that is a cut vertex. So since removing V disconnects the graph, then the only way that can happen is if one of the subtrees of V is what becomes disconnected, right? And if a subtree becomes disconnected from the rest of the graph, and then that means that there's no non-tree edge from the subtree to an ancestor of V. Okay, so that proves both directions of this lemma. And now let's see how we're going to use that. So we want now to make that lemma into a fast algorithm that will find the cut vertices. And the way we're going to do that is with a kind of helper function, which I'm calling low because that's the conventional name for it. The low value of a vertex V is the minimum of the discovery time of vertices W, where, so here's my vertex U in my picture. Either there's an edge from U to W, then I would consider the discovery time of W as a possibility here, or U has a descendant, here X, and there's an edge from X to W. Okay, so the interpretation of this is that the low value of a vertex V is how high up in the tree can we get by either taking an edge from U or going down from U and taking an edge up to some ancestor. Now, the one thing that might be slightly confusing is that I'm saying low, but I'm talking about higher in the tree. So you have to remember that what we're considering for the low value here is the discovery time, and those are lower as you go higher in the tree. So these are lower D values going up in the tree. And as I go down in the tree, I get to higher D values. Okay, so I hope that helps make sense of this, that low of U is how high in the tree, how low a D value can we get from the vertex U by going down 0 or more edges and then up 1 non-tree edge. Okay, so with this idea of the low function, we can reinterpret that lemma as saying that a non-root vertex V is a cut vertex if and only if V has some child where the low value is not higher up in the tree, not smaller than the D value of V itself. For example, here, the vertex 2 has a child 4, and what is the low value of 4? It's saying, how high up can I get by going down and then up one edge? And you can see that the lowest I can get, the highest up in the tree, is vertex 2 itself, and that's what makes vertex 2 a cut vertex, because of this child 4 that can't connect upward. Let's look at this example a little bit more thoroughly. I'm going to look what happens as time proceeds. In what order do I discover vertices and finish vertices and so on? So at time 1, I discover vertex 5. Then I discover vertex 2. I come down and discover its child 7. And now I jump out of this recursive call. I'm finished with 7. There's no more children of it. So I'm exploring some more from vertex 2. I discover vertex 4. Then I discover vertex 3. I discover vertex 1. And then I finish with vertex 1. So if I sort of mark the time when things are on the stack, this is what I've got so far. I finish with 1, I come and finish with 3. There's that. I finish with 4. Discovered 4, finished 4. Now this is the time when I finish with 2. I now discover vertex 6 and finish it. And finally, I finish with vertex 5. So this one comes all the way to this one. So there's our parenthesis system for this. If we, in order to compute the low values, right, we're depending on the discovery times. So let me write those down explicitly. For vertex 1, 2, 3, 4, 5, 6, and 7, what are the discovery times? Let's see. This I should complete the timing here. This is time step 3, 4, 5, 6, 7, 8, 9, 10. There we go. So I discover vertex 1 at time 7. Discover vertex 2 at time 2. Vertex 3 at time 6. Vertex 4, I discover at time 5. Vertex 5 is the first one I discover. Vertex 6 at time 12, and vertex 7 at time 3. Okay, and from this we can say what the low values are. And I'm just basically looking at the tree to discover this. So for vertex 1, how high can I get in this tree by going down? Well, I can't go down at all. I can only go up. And I get to vertex 2, and vertex 2 has a discovery time of 2. So there's, for vertex 1, its low value is 2. For vertex 2, how high can I get by going down and then up? Well, this way I can only get to vertex 2, but if I take this child, I can get up to vertex 5, and the low value of the discovery time of 5 is 1. So I have a 1 here. Vertex 3, I can get to vertex 2, but no higher up the tree, and discovery time of 2 is 2. Vertex 4, similarly. Vertex 5 is the root of the tree, and I cannot get higher than itself, and it has discovery time 1. Vertex 6, I can't get higher than 6 itself, and discovery time of 6 is 12. And finally, vertex 7, I can get all the way up to the root, and vertex 5, the root has discovery time of 1. So those are my low values here. And if we finally also look at the test that we should perform, according to the lemma, to know if a vertex is a cut vertex, we make this test about, does it have a child u whose low value is at least as high as d of v? So let's look at that test. If I test vertex 2, which we know from before, it is a cut vertex. So d of 2 is 2, and I'm looking at its children. And in particular, I will look at child 4 has a low value of 2. Vertex 4 has a low value of 2. And that is greater than or equal to the discovery time of 2, right? So then we would say that vertex 2 is a cut vertex. Okay. On the other hand, if I applied this test to vertex number 3, and note that the discovery time of 3 is 6, vertex 3 only has 1 child. So when I apply this test to see, I check all the children u, right? But in this case, there's only 1 child. Child 1 has a low value of 2. So the low value of vertex 1 equals 2. And that is less than the discovery time of 3. So 3 is not a cut vertex. Okay, so I hope that's a little more helpful to understand exactly what the low values are, what the discovery and finish times are, and how we use the low value to check the lemma. Okay. Here's how we compute the low value. When I'm looking at a particular vertex u, I do consider the edges from u to w and what is the discovery time of such w. But I also consider the low values of children of the vertex u and say, if I go to a child, how high can I go from that child? Now, notice here, X was not just a child, it was further down, but the recursive property will help us here, which is if I look at the child of U that leads to X, its low value will already capture this. So it suffices to look at the children of the vertex rather than to be considering all the descendants of the vertex. Now, the order in which this recursive formula should be applied is I have to know the low values of the children of a vertex before I apply this formula to compute the low value of the vertex itself. So I need to do the children, like to have the low values for the children before the vertex itself. And one way to do that is to order by the finish time, because if you remember how the depth first search works, it finishes a child of a vertex before it finishes the vertex. So inside the depth first search code, when we finish a vertex, we should use this recursive formula to compute the low value. I'm not going to give the details of doing that. I think this computation with low is complicated enough that I'm happy if you just have some understanding that there's a recursive formula and that we could compute that recursive formula inside the depth first search. I won't look at the details. I'll leave it as an advanced exercise for you. Now, supposing we do that, then here is how we apply the lemma and test if vertices are cut vertices. So I compute low as here, then I run the following test. I see, does the root have more than 1 child? Then the root is a cut vertex. And for every other vertex not equal to the root, I check, does V have a child where the low value is at least the discovery value of V? And if so, then V is a cut vertex. How much time does it take to do that? For every vertex V, I'm looking at all its children. And then I'm looking up in my pre-computed low values and my pre-computed discover values. So the time taken here is again this order n, the number of edges. For each vertex, I'm looking at its children. Actually, that's even only order n because I'm only looking at the children in the tree, and the tree has n-1 edges. Anyway, the runtime is linear for this. Now, so far what we've talked about is just finding the cut vertices, and what I claimed was that we could actually find the two connected components. And I will leave all of that also as an advanced exercise to actually find the two connected components. Okay, so then the summary of this lecture is we've talked about depth first search, about discover and finish times, and we've used depth first search to find cut vertices, and I've claimed you can also find the two connected components. What should you be able to do out of this lecture? Do a depth first search, understand it. What are the properties of the non-tree edges? As I mentioned in my first level summary. What are cut vertices of a graph? What are two connected components of a graph? And here I'm saying appreciate that depth first search can be used to find the cut vertices in linear time and the two connected components in linear time. And in the next lecture, we're going to look at depth first search for directed graphs. So see you in the next lecture.